Welcome everybody to this talk. My name is Walther Zwart. I've been developing software. I started developing software as a kid, as most of you probably did. Not very good software, but anyway, I started. I've been doing C++ for most of my career, working for these projects. I'd like to tell you all about them, but I'm afraid we'd run out of time. I'm now working at Optiver. I've been doing that for about 5 years. You probably heard of Optiver. We're a sponsor of the conference this year. Jens mentioned us. We have a booth downstairs. If you want to talk to us, you can come downstairs and there should be somebody there. So what does Optiver do? We are a market maker. That means we trade professionally on exchanges. And well, let's imagine you want to buy some shares, some Google shares, for instance. You go to an exchange, you want to buy them for a certain price, but there needs to be someone there that wants to sell them to you, right? Otherwise, you won't be able to trade. So we try to be that person. We try to have a good buying price and a good selling price for as many products as we can. So that anyone who wants to trade can come to us and trade with us. And even you might be saying, I'm not trading shares on an exchange myself, but chances are that some company that you're dealing with is trading on an exchange to provide you a service, like for instance your bank or your airline. So we're trying to make it easy for those companies to trade, making their process a bit smoother. Yeah, and that should improve the market, hence the name Market Maker. We've been doing this for a long time. We have 4 offices. Our main office is in Amsterdam. We have a lot of people working there. We also had a great talk this afternoon from Alex about benchmarking in trading and games. And we're also going to do a low latency C++ workshop in the conference in February, CPP on C. However, this talk is not about low latency. So this talk is about clean code. And why do we care about clean code in Optiver? Well, as I said, we try to trade as many products as we can on many exchanges with many traders. We have about 100 traders, 150 engineers. And this makes our whole system quite sophisticated already, that we're trading so many products, so many different types of products. And anything that we add on top of that just increases complexity and increases the chance of bugs. So when I was researching for this talk, I found this quote by William Morris. He lived way before computers were invented. But he said, you should have nothing in your house that you don't believe to be useful. And that goes for us as well. We should not have any components that we don't really need. We should not have any classes or any methods that we don't really need, because they just increase the chance of bugs. And it will slow us down if we want to change something in our code. Another quote from Uncle Bob, who is probably well known from his clean code book. It's not enough for code to work. It also needs to be maintainable and understandable. And so it will continue to work in the future. But clean code is a really broad topic. We could talk about it for hours, and let's not do that. So I wanted to specialize it a bit to a smaller topic, which is integers. And I chose integers for 2 reasons. First is that it's the most basic data type in the language, in C++. So I'm hoping that will limit our scope. And I'm also hoping that what we learn about integers can be applied to different areas in the language. And for the other reason I chose integers, I need to tell you a story. This happened about 4 years ago. I was already working at Optiver. I had a coworker who was really experienced. I considered myself a bit of a C++ expert, but he was a real C++ expert. He had been using it from the start of the language. He knew everything there was about POSIX and TCP and Unix, and yeah, he was really experienced. And one day he was chasing a bug. He fixed the bug, and then he sighed and he said, I thought I was a C++ expert, but I can't even remember the rules about integer promotion. And 2 thoughts went through my head when I heard that. The first was apparently he was not the expert I thought he was, because he didn't even remember the rules about these basic data types. And the other thought that went through my head was, what is integer promotion? I never heard of that. So I was not the C++ expert that I thought I was. And at least he knew what knowledge he was missing, and I had no idea what he was talking about. So let's do a little quiz about some of these rules. Not to prove that you're bad developers, but to prove that the C++ language has some rules that are not well known, and that can be quite tricky. So if you open the Kahoot website on your phone, we already have 36 players. Excellent. Oh, I've seen that name before. Indeed, it's not executed. It's just a declaration. Is anyone still trying to log in, or? Yeah, I'll give you some more time. So I'm going to show you 6 questions, and there's a time limit. And the speed at which you answer is important, because you get more points if you answer quickly. Let's give it a bit more time. Anyone still trying to log in? Shall we start? Oh, weren't we at 49? Oh, we're back to 49. Oh. All right, let's start. I think you can still join after we had the first screen. So we're gonna see the question here, and it's gonna move up to the top of the screen after a few seconds, but you should still be able to read it. So how many real integer types are there in C++? So please press the button with the right color. You have 5 seconds left. So the correct answer is 15. There's 15 real integer types, and I'll show them later. And there's also 30 aliases, which makes a total of 45, but the aliases are not real separate types, so 15 is the correct answer. Oh yeah. All right, so let's go to the next one. What will happen here? To make it clear, 256 cannot be contained in the 8-bit unsigned integer. So the standard specifically says what should happen in this case. So it's not implementation defined or undefined. And it also specifically says there's no overflow. It's just math. What kind of math? Modulo 2 to the power of 8 math. Okay, it's not really helpful that it's just math, but that's what the standard says about this case. So let's go to the next question. Again, 128 cannot be contained in a 8-bit signed integer. What's going to happen? Well done. So indeed, undefined behavior, which means that the compiler or the platform is free to do anything it wants to. It can completely remove the code or it might wrap around to minus 128, or it could crash the program or throw an exception, whatever it wants to do. And it can even do different things at different times. So there's nothing prescribed in the standard. Question 4. All right, so this is not overflow. And the reason for that is that operator plus isn't defined for 8-bit integers, but it is defined for regular integers. So both the operands will be promoted to a regular integer. So it will become an integer with the value 128. And then that gets converted into an 8-bit integer, which is not undefined behavior, but implementation defined behavior. The difference between that is that the compiler needs to specify what exactly is going to happen, and it needs to do the same thing every time. So it's slightly different. So still no HB who's on top. But there's only a close gap, so still exciting. So this line of code. What will be the type and the value of A? So, again, the plus operator is not defined for a character and a Boolean. So they both get converted into an int, so it becomes an int with the value of 66, because capital A has the value of 65. Of course, the real question is, why would you write code like this? But the real question is, why does the language even allow us to write code like this? Because I can't think of a use case for this. Oh, we have a new leader in the top 10. All right, last question. What is going to be the value of A? It depends. Oh, a lot of people got this right. So what does it depend on? Does anyone know?
Because of long and unsigned. It depends whether the unsigned can be, whether long is larger than unsigned, and then it would be implicitly converted.
Yeah, indeed, correct. So if the long can represent all the values that the unsigned can, the unsigned will be converted into a long integer. In that case, you will get minus 10 divided by 2, which is minus 5. But if the long cannot represent all values of an unsigned integer, the long integer will be converted to an unsigned integer, which will be, well, almost like on where unsigned is 32 bits, it will be 4 billion, somewhere around 4 billion. Then it will be divided by 2, so you'll end up with that big number there. But indeed, it depends on the platform that you're using. And I tried this on Godbolt. There's some compilers there that that return this answer, and well, my laptop returns this answer. So let's see what this does to the score. Okay, so we have a winner, MKL. Michael, maybe. All right, come forward. You can collect your prizes, and also the. Second and third place, we have a prize for you. So, all right, congratulations. This for you, and some a bag with some more goodies. So the second and third place, you can come forward if you want. All right, we have a bag for you. Congratulations. And third place or second. All right, yeah, well done. There you go. So,
can you please return back to the summation of these two integers? I mean, if I understood you well, they are being promoted to the larger data type.
yeah. Yeah.
Why is that?
I would say ask the committee. But
I mean, we have such restrictions in the automotive code, so obviously you cannot push anything that doesn't comply with the MISRA standard, for example. And although it is a C code and it has a bunch of the probably exactly the same rules, but I think I haven't stumbled upon that it would complain on the summation of two operands of the same type.
yeah,
It would if the resulting type would be larger, for example.
yeah,
So if the resulting type would be 32-bit integer, but the operands would be I don't know, short or 8-bit integers.
yeah. So in a lot of these situations, you do get the answer that you expect. Even well, yeah, I'm not sure about this one, but that's just because the implementation defined behavior that the compiler writers chose, they chose it in such a way that you get what you would expect to get. But the standard says you cannot add. Well, you cannot just add the 8-bit integers; they will be promoted to a regular int first. So, so what does this tell us about C++? It's that a room full of C++ developers cannot get all the answers right. It tells us that the language is quite complicated and that you need to learn about it. And last year, Kate Gregory, in her keynote, said you need to learn all of the C++ language. And I agree with that, but I would like to add, please avoid the obscure parts, because you don't know who's going to be reading your code next, and it might even be you in a few months, and you might not remember all these rules. So make sure you know where the pitfalls are, and please avoid them. So let's dive a bit deeper into clean code and integers. As I said, we can talk a long time about clean code, but I'd like to just state a few rules that we can apply to integers and that you can apply to other code as well. So the first rule of clean code is have a clear single purpose. Make sure that for every component in your system, every library, every class, there's a clear single purpose. A second rule is minimize the set of states in your classes and your components, because states complicate your code, and the nasty thing about states is that they multiply. If you have two components with both 4 states, that means that your whole system has 16 states. And if you have 3 components, well, you can see where it's going. It's going to explode. And you need to test all of them or make sure that they don't happen, or you need to deal with that. And also minimize the set of operations that you have available. Because having more code, more operations just increases the chance of bugs. And we'll go through some code to apply these rules and make clear how that improves your code. You might notice that I used the word clear in all of these rules. So let's talk about what clear means actually. So clear means it shouldn't raise any questions. If you look at the API, it should be it should not raise questions about what the intentions of the API is or what the purpose is. And even worse than raising questions, let's have a look at this piece of code. This templated print integer function, to me it makes perfect sense. It doesn't raise any questions. But if you call it with a 8-bit integer, do you know what you'll get? Who has done this? Yeah, you get a character. A, I think. You were close. So that's a surprise. That's a bad surprise, right? So it doesn't raise questions, but it behaves different than you expect. So raise no questions, give no surprises. So let's have a look at a small piece of code and apply these rules. No, there's no integers yet, but let's just see how we can use these rules to make the code a bit better. So we have a client class that is, it is pretty readable, I'd say. And let's apply these rules. So the first rule is a single purpose. I think it does that pretty well. The purpose is to get data from some system. So let's have a look at the states and operations. So what states can the client class be in? It can be default constructed, it can be configured, can be connected, and then after you call disconnected, it can be disconnected, which might actually be the same thing as default constructed, or it might be the same thing as configured. So it already raises questions, right? And it raises much more questions. For instance, what happens if you call configure twice? Will it throw an exception or reconfigure? Or what happens if you call connect twice? Will it create two connections? And as I said, after disconnect, do I need to call configure again, or will it remember the configuration? So it creates unclarity. And if you get a reference to this client, do you know what state it's going to be in? Or, well, you can get around the problem by adding a getter for the state, but that just complicates your code. So let's try to minimize the number of states and the number of operations and write the client like this. So we have a client, we pass in the config when we construct it, then it's immediately connected, and you can call get data on it. So there's only one state now, it's connected client, or maybe there's another state when after you destruct it or before you construct it. So no client. But at least if you have a client, then the state is clear. If you now get a reference in this function, then you know you can call get data. And the number of operations is also limited now. You can create it, get data, and then destroy it. So these rules, if you apply these first rules, it also removes all of the questions that we had before. So again, the rules summarized: single purpose, minimal states and operations, no questions, no surprises. So let's have a look at integers now and try to apply these rules. So as we saw in the quiz, there's 15 integer types. There's already 6 char types, which is already a lot, I would say. I think those are pretty much well known. And these are the aliases. So these are not different types, they are just aliases. So for the previous types, you can create one function with 15 overloads, and the compiler will accept that. That's what a different type means. And for the aliases, you cannot do that because they're the same type. Well, the same type as some other integer. So shall we go through these types and discuss all the 5 rules? That would probably take a long time, so let's not do that. And it's also going to be hard because what is this? Is there a single purpose to, let's say, unsigned long? Not really, right? It's more, the purpose of these types is more to represent the underlying hardware, your processor. But maybe we can turn it around. Maybe we can think about what we use integers for, and then think about which integers we can use for that, and if integers are actually the right choice for those use cases. So, who can come up with some use cases? What do we use integers for?
Length or something, or count.
Yeah, counts, yeah. Sizes. Anyone else?
Flags.
Flags, okay. You mean like bits and stuff like that? Yeah, okay.
Accumulation.
Accumulation, yeah. So mathematical operations, yeah. Okay.
Indices.
Indices, yeah.
Some sort of enumeration.
Some sort of enumeration. Yeah, like constants or, you mean?
Like a set of different states.
Okay. Okay, so we have a few use cases. Let's go through them and see how we can use integers and keep our code clean. So you said flags. I've called it bit manipulation. It's a simple use case, right? Every bit is going to be 0 or 1. So that's the range of states or values. Best integer type, I would say, is probably unsigned integers, because the shift operators are well defined for those. And the operations that we really need are bitwise OR, bitwise AND, XOR, NOT, left shift, right shift. Do we have other operations available? Yeah, basically all integer operations, right? Because yeah, the compiler doesn't see that you want to use this integer for bit manipulation, so you get all operations. So it's not really a strong type for the purpose. Can you come up with a stronger type for flags or bits? Yeah, I heard BitSet, and you said? Bitfields, yeah? Yeah, but those convert to integers really easily as well, right? So I don't think it would actually be stronger, but it can be used for bits indeed. But BitSet is indeed a stronger type. So if we look at some code where we could use a BitSet. So let's say you have some hardware and you want to set some pins, and you can set a single pin by calling setPin, or you can set multiple pins by calling setPins, and those pins are set inside an unsigned integer. And let's say we have this user code. So a user says the pins are 7, so he probably means 1, 2, and 4. And then he calls setPin. But wait a second, that's probably a bug, right? Because he said the variable is called pins, but the function that he calls is setPin. But what did he mean? Did he mean to call the first function with pin number 7? Or did he mean to set the 3 pins? So the compiler cannot help you here because it doesn't parse the name of the variable and compare it to the function. So if we use a bitset in this case to represent a set of bits, the compiler can help you, because if you call setPin now with a bitset, you'll get a compile error. So this proves that bitset is a stronger type and can prevent bugs. Unfortunately, the other way around, bitset doesn't help, because it can be implicitly constructed from an integer. It would have been nice if that was an explicit constructor. And there's another way in which bitset is stronger than an unsigned integer. Let's say we have this example. You want to set 24 bits, and you can express that in a bitset, but unfortunately, studuint 24t doesn't exist. So, conclusion, if you're manipulating bits, it's better to not use integers, but bitset if you can. So, this is a simple example. Let's go through the other types. Truth values. So the simplest integer type is probably a Boolean. Of course, it can be false or true. And the best integer type is a Boolean if you're handling truth. The operations that we need are AND, OR, and NOT. But what operations do we have available? Again, everything, because it converts implicitly to int and the other way around. It would have been so much nicer if that wasn't the case. And of course, we do write this code very often, but it wouldn't have been that hard to, it's not that hard to write it in this way. And this makes it a bit more explicit what you're trying to do. And Boolean also automatically converts to int, but I would say we don't really need that. Because do you ever do this? Add a Boolean to an integer? I don't think we really needed that in language. We could as well just write this statement, and if you look at the generated assembly, it generates exactly the same code. So let's have a little exercise with refactoring an interface that uses Booleans. So let's say we have a socket class, and we have some setters to manage the configuration. And the code that uses this is on the right. And it's all reasonable clear, but it has the same problem as we saw before with the multiple states and the operations. So let's try to refactor this a bit and create a socket class like this. So is this readable? Does it raise questions? I think the interface is pretty readable. If you see a string and an integer in a socket class, that's likely going to be host and port, right? And the names for the Boolean arguments are right there. So if you read this code, it's going to be perfectly readable. No questions. But if yeah. Yeah. Yeah, give me a second, I'll get there. So, but if you look at indeed the code that uses this API, it becomes unreadable because you don't see the meaning for the two booleans anymore, and you can easily swap them around. So it doesn't raise questions, but it does produce code that raises questions. So that's also a bad sign. And this also goes against a rule from Uncle Bob in the clean code book, where he says two parameters of the same type shouldn't be next to each other. And that's indeed what you said. It's easy to swap them. So let's change the API. Move the first Boolean one place up. And surprise, our code still works. There's no compile error. The 80 gets converted to a Boolean, so that becomes true. And true gets converted to 1, so we connect to port 1. So that's not exactly what we meant. So this rule from Uncle Bob is not even strong enough. So how can we fix this? Nowadays at Optiver we tend to use configuration structs a lot. This is also a rule from Uncle Bob. If you're passing in more than 3 or 4 parameters, you should try to create some structure in the parameters. So let's do this. So now people can just create the config struct, set all the fields by name, and that's going to be perfectly readable, right? Yes, unless when people use aggregate initialization, and then again, you're in the same place. And C actually already has the aggregate initialization with the field names, where you can say .host is localhost, .port is 8080. And I think that's been proposed or already accepted for C++. Yeah, I see people nodding. So we're going to have that as well, and that's going to improve this situation. So another way to fix this would be to make the Booleans different, make them a different type, right? For instance, by creating an enum for all the arguments. So this makes the API readable, because you can see exactly what the types are for the arguments, and the code that uses the API is readable as well. So it doesn't raise any questions anymore. Another way to fix this would be to use a strongly typed Boolean. Who knows what a strong type is? Or a name type, tag type? Okay, so for those who don't know, you can write a class like this, for instance. This just wraps a Boolean, but it's templated with a tag. And by giving it a template tag, it becomes a different type. And so it cannot be constructed from a Boolean with a different tag name. Then this constructor doesn't exist. So you can't easily mix them up. You cannot create a Boolean with one tag from a Boolean with another tag. So that's what it means to be a strong type. And this code is actually enough to enable these interfaces. So if you need this in a lot of places in your code, you could use this pattern. And then all you need to do is where you accept the Booleans, accept a strong Boolean with a tag. You can even forward declare the tag right in the API. And then the code that uses that also becomes, there you also need the tag, which makes the code more readable. At least if you know the pattern. If you see this for the first time, you might think, what's going on here? But it might be worth it for your code base. So conclusion here, don't use Booleans unless the function name makes it clear what the Boolean is for, or in other words, unless it's the sole argument. So let's look into text manipulation. This is a use case that wasn't mentioned just now, but it is also, these are also integers. I don't want to get into this too deeply because when you're handling text, you should probably be using UTF-8 and or UTF, and that's a really big topic. And to be honest, I don't know everything about that, or maybe I don't know much about it. So the best integer type is usually char. What operations do we need on this char? Do we ever need to subtract 5 from a curly brace? Or multiply the character a by 2? Or add an integer to the 0 character? Has anyone done that? Yeah, exactly. Yeah, so this is a valid use case. When you're doing string parsing or formatting, you're going to do something like this if you want to do it fast. But if you think about it, it's not. This is only because someone was clever enough to put the digits in the right order in the ASCII table, right? Because a char is just an index into the ASCII table. And for UTF text, it's more complicated. It's not even an index, but it's a whole different thing. So it's not really a numeric type. You shouldn't use these. Well, you should use this this trick. It's fine to use that, but it shouldn't be this easy to use this trick. The language shouldn't make it this easy for us because we can mix it up. So I would say the only operations that you really need are comparison. And you could talk about smaller than, less than. But that's actually debatable because the order of the alphabet depends on the language. So that's also a big topic. So, and of course there's also a stronger type, which is string. And it's no surprise that string doesn't support mathematical operations because they don't make sense for text. So, another use case is numeric identifiers like database IDs. And yeah, the range and the integer type depends a lot on how many of these IDs you're going to have and where you're going to store them. The operations that you need on them are again comparison and maybe ordering if there's a logical ordering in them, and maybe plus plus to get the next available ID. But not all of the other operations, no bit manipulation, no mathematical operations. If you're doing that, you're probably doing something wrong. And this is another case where usually when you're comparing IDs, you should only compare them to IDs of the same type. You shouldn't compare a company ID to an employee ID. Like for instance, if you have this API, if you use an unsigned integer, you can easily get this wrong, right? If you call it this way, the compiler doesn't see that the first one is an employee and the second one is a company, but it should be the other way around. And you can already see this because this argument got a name for the variable. That name there means that the writer of this API tried to convey some information to the user that the compiler doesn't check. Because that name, company ID, tells the user this is about a company, but the compiler doesn't read variable names. So it should already be assigned. If you need to specify a name here, you're probably not writing the cleanest code you could. So similar to the strong Boolean that we had before, we can write a strong ID, which is also can be really simple because it doesn't need to support all of the mathematical operations, just these three. And then let's say it looks like this. Now the compiler will be able to help you. It will give you a compile error. So conclusion, if you can, use a strongly typed ID class to prevent bugs. So let's look at the last use case for I grouped indices, amounts, and numerical calculations together. So what's the most natural range for amounts? It's all non-negative numbers, right? You cannot have -5 cows or something like that. So the most natural integer type would be unsigned. And the operations that we need are all mathematical operations. no bit manipulation, no Boolean operations. But here we do get into a tiny issue that as soon as we start subtracting amounts, we might end up in negative territory. And there's a way to prevent that. So let's have a look at difference types. What do you get when you subtract two dates from each other? When you get the distance between two dates? It's not a date, right? It's something else. Or two stud chrono time points, you get a duration. And two pointers, if you subtract them from each other, you get a pointer diff t. So I would say if you subtract two unsigned integers from each other, you should get a signed integer, right? Because there's a 50% chance you'll end up with a negative number. But unfortunately, the language doesn't support that. It does understand it for the other types, like, so for the chrono example, the standard library understands this concept. And for the pointer example, even the language understands the concept of different types. But for unsigned integers, we don't have that concept. And since it's so easy to end up in the negative range, I would actually like to do this again. So the range of values is actually, the chances are really high that you're going to end up in the range like from minus infinity to plus infinity. So the most safe integer type would be integer, or maybe a 64-bit integer if you need a range. You could go lower as well if you're storing the integer. It makes sense to pick a smaller integer type. But if you're not storing it, I would just go with int. The mathematical operations are still there. We need those. So you might have some objections against this. So let's go through them. You might say, I need a positive range of unsigned integers because if I take an 8-bit signed integer, it only goes to 127. And that could be true for your case. And for small integers, I can believe that. But for 32-bit integers, it's quite unlikely, right, that you can solve your problem guaranteed within 4 billion, the range of 4 billion, but not in the range of 2 billion. That's quite unlikely. So it might be true for some cases, indeed. You could also say 0 does express the 0 as the minimum does express the actual range better because like for amounts and indices you can't go below 0. That is true, but it's also really scary, as I already explained with the subtraction, because if you use unsigned integers, it's like you're standing at the edge of a cliff and when you're at 0 and there's 4 billion safe steps you can go in that direction. But you choose to jump around here, like next to the cliff, and there, when you go off the cliff, yeah, you don't know what's going to happen. But you might say, well, what's going to happen is defined behavior, so that's good. And that's true in some cases, but what are you going to do with this number that you get? So you underflow, and you get a number in the range of 4 billion. But then what are you going to do with that? Are you going to use it to index an array? Then you're still going to get undefined behavior. And in our case, if you're going to use that number to calculate a price to sell something on the market or to buy something, you will get defined behavior, but will go bankrupt. So it's not going to help us very much. And this is an example where this indeed leads to undefined behavior. This code looks fine, but if you call it with an empty container, the size -1 is going to underflow, and it's going to be 4 billion. And then you index the array out of range, and you get undefined behavior. And this particular example would actually work if size would return a signed integer, or if size t was a signed integer, because then it wouldn't even start looping over the array. But you're going to say size t is unsigned, and the SCL uses it everywhere. And that's a good point. And I found this video online from CPPCon a few years back, where there was a panel with a lot of C++ committee members. and then I said this. The STL is wrong and we're sorry about it. But the fact is still that we are stuck with this STL. And so how do we deal with this? So there is a stronger type for indexing containers from the STL, and that's iterators. Iterators don't support all the operations that the integers have if you use them for indices. And if you subtract two iterators from each other, you get a signed type pointer diff-t. So that does support these concepts better. And also convert to signed quickly as soon as you can, because when you mix signed and unsigned, you get these problems that we saw in the quiz in the last question. So another question is how to prevent this undefined behavior or unexpected behavior. Well, we could have multiple talks about it, but let's just have a look at the small piece of code and see if we can prevent all unexpected behavior in there. So there's a few bugs in this piece of code. Who can point one out?
Divided by 0?
Yeah, division by 0. Which happens when you call it with an empty vector, right?
Possible overflow.
Yeah. Of total, yeah. Okay. Another one?
Integer type division, we need to divide totally by size.
Yeah.
So it will use the integer number, not the floating number.
Yeah. True. What kind of integer will it return? It depends, right?
I guess the same as total.
Sorry?
I guess the same as total, so it will be integer 32-bit string.
Well, if size returns something that can be expressed in the type of total, then it will return the type of total. But it's likely that that is not the case, because that vector returns size t, which is usually 64-bit unsigned integer, right? So it will actually return an unsigned integer. So let's fix some of these issues. So yeah, indeed, the division by 0. Let's check right away if values is empty and throw an exception. So we've taken care of that. Then we also have the overflow in total. So let's make that a 64-bit integer. That's a bit safer. Doesn't take the overflow completely out of the picture, but let's look at that later. And I fixed the return type to a 32-bit signed integer. And I was hoping that this statement at the bottom would give me a warning. So I enabled all warnings that I could think of. W all, W pedantic, W extra, W conversion. And I didn't get a warning. And it's actually really bad because it not only does it return a different type, then you would expect it will also return the wrong value. If you call this function with a vector that contains two negative integers, you'll get some huge positive value. So even this simple code is wrong, and I don't get a compiler warning. So again, that shows that the C++ language is a bit too complicated in some cases. So let's fix the type issue. And let's apply the rule that we just had, convert to signed quickly. Does this fix this problem? Could it ever happen that size doesn't fit in a signed 64-bit integer?
Theory, yes. On 64-bit architecture.
Yeah. Could happen. So should we maybe add a check to make sure it doesn't happen? Will we ever get there? If the size of the vector doesn't fit in a signed 64-bit integer, how long do you think we'll be running this loop a few hundred years probably. That would suck, right? We would do calculations for a few hundred years and then get an exception. So chances are your code is not going to be running this long. So let's just remove that check. But total could still overflow, right? The 64-bit integer. If you have enough big numbers, could go wrong. So can we check the overflow like this? Any problems? I don't think this would work, because total plus v, that can never be bigger than the max signed integer, right? So in the check, before we actually finish the check, we already overflowed, and we won't actually get the exception. So should we maybe move v to the other side of the comparison? Would that help?
V might be negative.
Indeed. If v is negative, then max minus v is going to overflow. So maybe something like this then? 2 checks. I think this would work, but it's not very pretty. So manual checking is really hard, and it's easy to get wrong. So use the tools you have available to help you with it. Use compiler warnings, static analyzers, and maybe also better is a library solution. And we could use multiple libraries for this. Boost multi-precision, for instance, would help us with a type that doesn't overflow. And even so, if we choose a type for total that doesn't overflow, when we divide it by the size here, we are sure that it will always be in the range of a 32-bit integer, right? Because it's the average of all the numbers that we have, so the average can never be out of range. So we only need a multi-precision type there, and not in the return type. Numeric conversion will also help you with overflow situations, because it will check if you could actually represent the value in the new type. And I have Boost Safe Numerics here, but as Andre said in his keynote, there's multiple libraries that do this, and they will just help you prevent the errors that we discussed. But it's a lot harder than you might think at first. So conclusions. Raw integers in C++ don't do a good job of limiting the states and operations that are available. And I used the word raw here to make a connection with the raw pointer, because we should be we should have this habit of whenever we write a raw pointer, that should trigger something in our brains that makes us think, do we really need a raw pointer here, or should we use some other type? And I would like to have the same trigger for raw integers. Should we really use this raw integer, or is there another type, a stronger type that we can use? So use the strongest type you have available, and strive for no questions, no surprises. Questions? You realize that if you ask a question now, I will not achieve my goal of no questions. So think before you ask. No, go ahead. If you have a question, let me know.
Did you measure any performance implications of using these library solutions?
Yeah, so the question is, thanks. The question is if there are any performance implications to using these libraries. Yeah, there's always going to be some performance implications, right? I think safe numerics is pretty efficient, and it doesn't do any checks if it can see that it doesn't need to do that. But there's going to be some checks executed at runtime. But I don't expect it to be worse than doing manual checking, because if you want to prevent overflow, you'll need to do that yourself. And Boost multi-precision, yeah, again, it's hard to compare it with using regular integers because they don't do the same thing, right? Because if you use a regular integer, you need to check yourself. And you won't be able to do the multi-precision. But I think these libraries perform reasonably well. No other questions? Okay, thanks.